recorded. Okay. So today I'm going to use this app, this note taking app to do this course. So today the lecture topic is electromagnetic wave. During the past courses, we have gone through basic points in electrostatics, magnetic statics, the energy of electromagnetic field, and propagating electromagnetic wave in transmission line. Today, our focus moves to the electromagnetic wave in free space without any charges and current, which is a very clean setup, but very useful and informative about electromagnetic field. This is outline today, consisting of 4 bullet points. We were starting from Maxwell's equation and derive the space and time relationship. And then to simplify the discussion, we will see the 1D case first and come back to the 3D case. Next, to get the clear physical picture, the interpretation of EE, more specifically, the complex analysis will be borrowed to rewrite the Maxwell's equation in wave propagation terms. Okay, let's start. So everything in this field can be derived from Maxwell's equation. After finishing this course, like you can forget like anything but these equations. So please let me write down the Maxwell equations in media first, together with constitutive relations. Oh, oops. So this is just a quick review to the first lecture. To make these symbols more organized, I will also write down what physical quantity these symbols represent. So here the E is the electric field strength. The B is the magnetic flux density. D is electric flux density. H is magnetic field strength, and we can relate them through the constitutive relations. Here, the epsilon is permittivity, and the mu is permeability. And remember, the rho represents the free static charge, and the J is the free moving charges, so basically free current. So the Maxwell equations are very beautiful, but for a person with OCD like me, they are not perfect at the first look. because they are not strictly symmetric. This is due to the non-existence of magnetic monopole. So we might as well to get rid of these charges and current. So if without this, we can get Maxwell equations in media like this. Now I feel much more comfortable. So look at these four equations. The first one say the curl of the electric field equals to the minus time derivative of the magnetic flux density. The second says the curl of the magnetic field equals to the time derivative of the electric flux density. The third and fourth tells us the divergence of the electrical and magnetic field flux density equals to 0. So the last two basically tell us the electrical and magnetic field has no source. And the first two can qualitatively describe how the electrical magnetic field propagate. Like the dynamic magnetic field will generate the electric field, and the time varying electric field will generate the magnetic field in turns. Just use your imagination. It's like two people. One push another forward, and the other will pull the one like forward as well. So these two can give the qualitative description of how the electromagnetic field propagate in the media, but we want a more like accurate description. So let's do it. Since you look at these four quantities, the E, B, D, and H, the D and B is basic like the alias of E and H. So to make this Maxwell equation more like concise, I will do some substitution. So these four can be first become and we can, I want to label them as 1, 2, 4. So 4 equations, 2 unknowns. We can easily like derive one equation only contain a single like variable. So look at the first 2 equations. We can look at the second equation first. The left hand side of the second equation contains the H, and the right hand only contains the E. So we can try to create a same expression of the left hand side of the equation 1 and substitute the 1 to the equation 2. So we can get an equation only contains the H. So I want to write following this. So we can take the curl to the both side of the equation 2. And according to the vector analysis, the left-hand side of this equation can be written as And for the right-hand side, we can exchange the Nobler operator and the time derivative. So we can get, okay, that's good because now we can use the equation 1 and equation 4. Then we will cancel out this term. Okay, great. Here we are. We got equation only contains the edge. So this is a PD about edge. Since the E has a symmetric position in these 4 equations, so similarly we can also get an equation only contains E. So let's look at these 2 equations. These 2 equations are the most important equations today. The left-hand side, this is a Nabla operator square. So it's not the simple like special gradient anymore, but it is the second derivative in space. This is also called the Laplacian operator. And the right-hand side, it is a second order time derivative of the E. So to sum up, the left-hand side tells us the spatial distribution of the electric field, and the right-hand side tells us the time information about the electric field. So these equations relate the time and the space. Time and space is a very important pair of quantity in physics. So I want to mark here, this is a spatial, and the right-hand side is temporal. Okay. I want to copy it here because they are very important, and our discussion will around these 2 equations. So I want to give more information about these 2. These 2 equations belong to a more general PDE family. It's called wave equation. The wave equation is a very important second-order linear PDE in physics. It has been studied for a long time. So in the history, it was studied by the mathematicians first. Its 1D case was studied by a mathematician called Lambert in 1746, and its 3D case was studied by the famous Euler. If we're using the notation of the Newtonian mechanics, we can write it as So here's this two dot represents the time, like second order time derivative. And here the c is the non-negative constant, like it usually refers to the wave speed. So these equations can be easily derived from the mechanical wave or even from the Hooke's law to describe the moving spring. So to express our equations in the form of this, I need to rearrange these equations, these two equations, like we can written it as, okay, they are now, their expressions are unified. So compare these two, we will find this. So, oh, hi. Do you have any question? Oh, okay. So here we can relate the wave speed to our two quantity, the permittivity and the permeability. This is a very interesting equations because basically it tells us like even the wave doesn't exist in the media, you can still tell the speed of this wave because it's only dependent on the characteristic of the material, but not anything else. So for electromagnetic field, if you consider our equations in the vacuum, so the C will become this. So basically, this is just a light speed, is an electromagnetic speed. So here we get this speed from this analogy, but I want to get a more mathematically rigorous derivation later, like only from the equations we got from here. So now, because since these two equations are in 3D space, it's a little bit complicated. So let's simplify it first. Well, we can discuss the 1D wave equation first. So if we have a 3D space, now I want to cross out these two. So we only focus to the x-axis first. So I can write the electric field as this form, right? Then we substitute this to the equation we just got. We can get the okay. This is the x represents the both sides are vectors, but clearly the magnitude should be the same. So now let's think of the wave speed. Normally, how to define speed. Like it's related to the distance and related to time. So we can define the speed as this, the distance divided by the time. So here the c is just a constant. It doesn't refer to the light speed. It's just a common speed. So we want to have this kind of factors in our equations, so we can find the relations of this equation to our light speed, our wave speed. So we can use the chain rules to the right-hand side. Okay, let's check it. Like if you cross this, cross this, cross this, these two are exactly the same, right? So, but we want to get the factor like this. So we have to write the equation like this to have the speed. Okay, so we can put all these constants outside. Oh, finally we arrived to this. It's clear we can cross out these two terms because they are exactly the same. So finally we can got this. It says wave speed square equals to the inverse of the inverse of the product of the permittivity and the permeability. So this result is the same as the one we just got from this analogy between our equation to the general form of the wave equation. So we can tell this is true. Next question is how can we solve this equation, this 1D wave equations? Thanks to the mathematicians, like they have helped us to solve these equations. So I just want to directly introduce this. Like, if we want to solve this, we need to define two new quantity. So let's write the 1D wave equations first here. Since like it's a 1D equations, we can cross out this direction vector first. And to make the equation more concise, we can use the wave speed to replace these two quantity. It will become like this. Now we need to define two more new quantity. Like one is we call A. Yeah, this just random pick variables. It doesn't have any meaning. x plus ct. Now we calculate this to a partial derivative. It can be written as still, this is just chain rule in derivation, right? B. Since the coefficient in both equations of the x is 1, so this can be written as this, because this is 1, this is 1. Okay, so finally we can write this as like this. And similarly, we can do the second order time derivative to the second term. We can get okay. So I mark this as 6 and 7, and we put the 6 and 7 to this 1D wave equation, the equation 5. We will get this zero. So if we integrate this left-hand side to the A, we will get the issue equals to a function of B. If we continue integral this equation to B, it will comes out. So you can check. If you take the second derivative to the E, then you can guarantee this gonna be 0. So this equation tells us the general solution of these 1D wave equations will be like this. So if we draw a graph to this function, like let's say since the fx can be an arbitrary function, so I just draw some random line to represent this is fx, the same as gx, and the ct term will tell us the fx we're moving like right hand side in a speed of c, right? And the gx we're moving left with a speed of the c also. So basically, this tells us the general solution of this 1D equation can be written as the sum of the two left traveling function and right traveling function. Then traveling means the shape of these individual arbitrary functions with respect to x stays constant. So and the speed of these two functions should be the speed c. This result coming from the mathematician I mentioned before. Like it was derived in the 1746, and this result remind me of the solutions to the transmission line. But in transmission line, you have the boundary conditions and you have the attenuation. But in our case, the fx and the gx won't be attenuated, and it will propagate from the negative infinity to the positive infinity. So this is a general solution to the 1D wave equations. And fx, gx are basically arbitrary. But we can have a particular solution, like have more physical meaning. So the particular solution to these 1D wave equations, we want to read it as this form. So E equals to E0 E I omega t minus kx. So how can this be related to the general form? So I want to rewrite this a little bit. Ik minus kt. Okay, you can check. These two should be the same. So compare this to this general solution form. You will see this omega over k will equals to our wave speed. So what's the physical meaning of this omega and k? The omega is the angular frequency of our wave, and the k is our wave number. They can be further written as this. So I relate omega and k to our time frequency and our wavelength. So it will become f lambda. Or we can further written it as this. This is a time frequency times the wavelength. If we written it as this becomes our spatial period. And the t will be our temporal period. So this relations tells us the speed relate these spatial and temporal quantities. I want to give this because I want you to always remember this duality between the space and time. It will very helpful to remember all these relations between these quantities. So if our particular solution can be written as this form, we can substitute it back to our wave equation. So we can gate. Oh, first let me rewrite the one D wave equation first. Then we put this to the wave equations. We can get the forms like E minus Ki square minus E minus I omega square. Because the exponential function, if you take the derivative to the exponential functions, it will stay the same. And according to the chain rule, you only put the coefficient of this variable x or t outside. So if you take the derivative once, you put this coefficient outside once. If here we take the derivative twice, so we have this coefficient by 2 times, like we have 2 coefficient outside. This is very straightforward. If we first rewrite this, and we can get these relations. So look at this. So they are the same, right? So we can written this as, yeah, if we introduce the wave speed, we can get the same conclusion as before. So the speed is only dependent on our mu and epsilon. Okay, this is all for the 1D wave equations. And similarly, we can generalize this to the 3D case. But this way, we gonna use the vector product. So we can write the particular solution to the 3D wave equations in this way. We only change here. Here is the vector product, the inner product, or the dot product. And then if we substitute this particular solution back to the 3D wave equation, where is the 3D wave? Oh, here. Similarly, we can get the final result as this. C equals to the inverse of the square root of product of the mu and epsilon. So I won't repeat this process, but I just want to, I will encourage yourself to do this. Like, it's very straightforward. So next, we want to rewrite the Maxwell equations to get more information about the electromagnetic field. So for that, I will do some mathematics first. So let's calculate the left-hand side together, like how to do this divergence to the electrical field. Okay, so if you look back the lectures in first class, we already give the definition about this vector analysis operator, that's the Nobler operator. So it can be written as this. Since this Nobler operator only with respect to the space, so only respect to the x, so this time term can be treated as a constant. Okay, so if we proceed the calculation, so basically we take the we can also expand this to make it more clear. This should be right. So because this is the dot product, so you can write it as this. So we just take the derivative along the three axes to this quantity. So we can get minus ikx plus minus iky plus minus ikc e minus ikx x. Oh, and also remember to don't omit this three directional vector. So it should be here. Let me rearrange this. This will become this. Right. So the kx, kyy, and kzz basically is just the k vector. And I rewrite this sum back to the vector form. So finally, we will get this as E. So this is just, so as you can see, if we take one Nobler operator on E, we just put out the minus ik. This is our conclusion. If you calculate this, it's very straightforward. You can do it by yourself. We just take out these terms twice, so we can get the square of it, multiplies the E. The same as this time derivative. So if you take the one time derivative of E, you will put out this I omega. So summarize it, the Nobler operator is equivalent to the minus ik, and the time derivative is equivalent to multiply with I omega. So these two will help us to simplify the Maxwell equations. and to find the relations between the electric field and the magnetic field. So now let's look back. Come back to this. Copy. With these two relationships, we can rewrite this as minus k. Oops, I've got to give one more relations. If you cross product with Nobla operators, you will get the I minus ik product cross product with quantity. So here this will be and this will be okay. Since all these four quantities, the E, B, D, H can be a complex number. So because in our particular solution here, the E can be a complex number. So I wanted to add this notation to represent these four quantities can be a complex number. So let's look at these four equations. We can cancel out this imaginary constant first. So this cross product tells us, according to the linear algebra, the KEB will form a right-hand coordinate system. So it says the B will orthogonal to the plane consisting of this K and E, right? And let's look at the third and the fourth equations. The K, the dot product of K and D equals to 0. It means the K should orthogonal to this D. The same as the fourth equations. This K should orthogonal to the B. So if we combine these three relations, we can tell this, the K should be orthogonal to both D and H. K, D, B. Okay, we can use, since the D is equivalent to E and the H is equivalent to the B, only with the difference of one constant, one coefficient, right? So we can get these relations. Also, D and H is perpendicular to each other because of this. The final comes from this. The final relation comes from the first equation. So we can draw a figure to illustrate the relations between among these three quantities. Remember this cross product will follow the right-hand coordinate system. So if this is K, this is E, the direction of the B should be upward. You can use your right hand like, wait. Oh, no. Sorry. This is E. Okay, so you can use your right hand. You wipe from K direction to the E direction, and your thumb will point to the direction of B. So the direction of B should outward from the paper. So this should be the B direction or edge, whatever, just different quantities. So let's look back to this triangle relations. K actually is our propagation direction of wave, and the D is electric field direction, and the H represents the magnetic field directions. So from this, we can get the full description of the propagation direction of the electric field, magnetic field, and this wave field. And from these four equations, another significant observation is the E and H are in phase. This needs some mathematics, so I want to prove it here. Let's. Okay, this is what we got. So from the first equation, we got and use the constitutive relations. Get this. To reveal the spatial relations between these quantities, I want to define the three directional vector. This is K, I call it E1. Its directional vector is E1. And this should be E. And its directional vector is E2. And this is H. Directional vector is E3. Okay. So now I can write the K, E, and H as follows. The K can be written as this amplitude multiplied by this directional vector, and the E can be written as multiply here I add a phase term, because at first we don't know if this E and H are in phase. So I just add a random like a phase term in the expression. Then if we want to prove they are in phase, we just to prove the random phase should be the same for both E and H, right? So same as H. But this is EH. And its directional vector should be E3. Then we look at the left-hand side. It should be the KE0 EI. And the E1 cross product E2 should be E3. And right-hand side should be this. So these are two complex numbers. They are equal to each other. So their amplitude and the phase should be equal simultaneously. So let's circle out their amplitude and phase. Since these two terms are the same, I just cross them out. Phase. So it should be we get this. Okay. So from the second equation, we know the E and H must be in phase because these random like phase term are equal to each other. And so what does the first equation tells us? We can rewrite it a little bit. It should be. So basically, this equation tells us the relations between the amplitude of E and H. So the amplitude of E and H can be a random number. They have to satisfy this relationship. So if you know E and you know K, you will know H. So the KEH is like a coupled quantities. These three quantities, if you know two of them, you will know another. So to sum up, starting from this part, we can get the three important conclusions. One is the K is orthogonal to the E and H. So it says the electrical magnetic field is the transverse wave. And second is the KEH forms right-hand coordinate system. And the third conclusion is the E and H must be in phase and their amplitude should satisfy this. Okay, that's all. Like this lecture, we deduced the important wave equations, these two, and we give the general solution and the particular solution to these wave equations. General solution is this equation, and the particular solution is this form. And we rewrite the Maxwell equations using this complex analysis expression. Why we can substitute the Nobler and the time derivative in this way is because we calculate it and we find it we can do this. So we from this rewritten Maxwell equations, we can first derive the relations between the K, E, and H. Finally, we get these three important conclusions. So the key takeaways for this lecture is basic, marked by the stars. So 1, 2, 3, and certainly these wave equations. Yeah. So basically, this is all for this lecture. If you have any questions, you can raise it now.